Good morning, students. In this video, I would like to discuss with you about registers. As you all know, a flip-flop is a one-bit memory cell which can be used for storing digital data. It can store only single data, either 0 or 1. So, to increase the storage capacity in terms of number of bits, we can use a group of flip-flops. Such a group of flip-flops are known as registers. So, the registers are small memory locations to store digital data, for which we can use D flip-flops. The advantage of D flip-flop is that it has only one input. When D is equal to 0, we get output as 0. When D is equal to 1, we get output as 1. So, we can store 0 and 1 in D flip-flop. An array of flip-flops used to store the binary information is called registers. Each flip-flop stores 1 bit information. Therefore, n-bit register will consist of n number of flip-flops and is capable of storing n-bit word. Generally, registers are used for temporary storage of data of binary information within a digital system. So, I already discussed we are using D flip-flop to store 0 and 1. If we apply binary 1 as input and clock pulse, this D flip-flop can store 1 or it will go to Z state. When the input 1 is removed, note that flip-flop remain in the Z state. That means it will retain its previous output. So we can store 1. Then shift register is a group of flip-flop used to store multiple bits of data. The bits stored in such registers can be made to move within the register, in and out of the register by applying clock pulse. It can be moved from left to right or from right to left. Therefore, it's called shift register. Shift register is classified into 4 types: serial in, serial out shift register, SISO, serial in, parallel out shift register, SIPO, parallel in, serial out shift register, PISO, and last one, parallel in, parallel out shift register. So, first one is serial into parallel out. The registers is loading with the serial data, that means 1 bit at a time, 1 by 1, with the stored data being available at the output in the parallel form. That means simultaneously we will get output, but data will enter 1 by 1. Serial in to serial out, in which data is shifted serially in and serially out of the register, 1 bit at a time in either a left or right direction under clock control. Therefore, serial means 1 at a time, parallel means simultaneous. Next, parallel in to serial out. The parallel data is loaded into the register simultaneously. Parallel means simultaneously. And is shifted out of the register serially. That means 1 by 1 under clock control. And last one is parallel into parallel out. The parallel data is loaded simultaneously into the register and transferred together to their respective output by the same clock. So, parallel in, parallel out. Simultaneously, we can enter data and we can get data simultaneously. The first one is buffer register. It is also called parallel in and parallel out. That is the simplest register. So, I am discussing parallel in and parallel out register first. It is also called buffer register. Buffer register is the simplest kind of register and store digital word. A 4-bit buffer register which contains 4 flip-flops to store a 4-bit binary word. A D flip-flop can be used to transfer data from input to the output. 4-bit buffer register is a sequential logic circuit with a 4 D flip-flops because we have to store 4 digits. So we are using 4 D flip-flops. It is also called parallel in to parallel out. This is the logic diagram of parallel in, parallel out or buffer register, in which we have 4 inputs D0, D1, D2, D3 represented by B0, B1, B2 and B3. B3 is the most significant bit and B0 is the least significant bit. Then outputs Q0, Q1, Q2, Q3. And we are giving a common clock to all the flip-flops, all the D flip-flop. Then inputs, a single input, B3 to D3, B2 to D2, B1 to D1 and B0 to D0. And outputs are taken as Q0, Q1, Q2, Q3. So when a positive edge of the clock is triggered, then the flip-flop get loaded with the input binary bits simultaneously. Therefore, it's called a parallel in. The loaded bits appears at the output simultaneously, so it's called parallel out. Only the clock pulse is essential to load all the binary bits. So suppose initially Q0, Q1, Q2, Q3 are SISOs, then apply data to be stored at the input terminal D3, D2, D1, D0, and let's say the data which is to be stored is 1010. Then let us check the working. So this is the input session. We are giving the data 1010. We want to store this 1010 into these D registers. So when we are giving a clock pulse, suddenly all the data gets stored here. B3 stored here and get us Q3. B2 0 stored here and get us Q2. B1 stored here and get us Q1, and B0 stored and get us Q3. Q0. So D0 0 stored in this flip-flop and get it at Q0. So in conclusion, there must be one flip-flop for each bit in the binary number. Simultaneously, D0, D1, D2, D3 was applied and loaded into Q0, Q1, Q2, Q3 by single clock pulse. See this. We are applying data. Then we are giving a clock pulse. Simultaneously, all the data will appear in the output. Therefore, it is called parallel output. We are entering data at a time. Therefore, it is called a parallel in. Therefore, this register is called a parallel in, parallel out, PIPO register. Next is serial in, serial out shifted register, SISO. The shifted register which allows serial in one bit after the other through a single data line and produce a serial output is known as serial in, serial out shifted register. Since there is only one output, the data leaves the shift register one bit at a time in a serial pattern. Thus, the name serial in, serial out shift register. This is the logic diagram of serial in, serial out shift register, in which the data will be entered in a serial manner. Therefore, we have only one input, and the output of the first flip-flop is fed to the input of second, then the output of second to third, and the output of third as the input for the fourth. Therefore, data will be entering from left side in a serial manner, and we have only one output because this is a serial in and serial out register. and we have a common clock line here. These all are D flip-flops. So let us consider the condition in which Q3, Q2, Q1, Q0 are zeros. Then we have to enter the number 1111. And D3 is connected to a serial data input DIN. The output of FF1, that is Q3, is connected to the input of the next flip-flop D2, and so on. So before applying of clock signal Q3, Q2, Q1, Q0 all are zeros. Now we have to store 1111. So we are giving the first least significant bit 1 on the left hand side of this circuit. I will show it. So the data which should be stored is 1111. So first of all, I am giving this one here. We are entering in a serial manner. When I am giving the first clock pulse, 1, this least significant bit appears here. Then second, this bit from here shifted to here, and next most significant bit appears here. See, in the next clock pulse, see this. This shifted from Q3 to Q2, and a new bit appears here. So before applying of the clock signal Q3, Q2, Q1, Q0 are zeros, then after first clock pulse, the output will be 0, 0, 0, 1. As soon as the next clock gets triggered, the output will changes to 1, 1, 0, 0. Okay. Then third clock pulse. When I am giving the third clock pulse, this one shifted to here and this one shifted to here, and a new one, that is next one most significant bit, appears here. See, when I am giving a clock pulse, and when I am giving another clock pulse, most significant bit appears here, and all other bits shifted one place to the right. So after third clock pulse, output will be 1110, and after the fourth clock pulse, output will be 1111. That is our requirement. Therefore, all the data will be entered here. So in order to get the output, we have to give clock pulse one by one. After the fifth clock pulse, we can get this 1 from Q0, and after each clock pulses, we will get the next significant bits. So when all data has been fed into the device, the clock is stopped. The data can be stored for any length of time during which clock pulse is absent. To bring the data out of the register, they must be shifted and taken off the Q0 output. Serial in parallel shift register. This is the third classification. In such type of operations, the data is entered serially and taken out in parallel fashion. Data is loaded bit by bit, and output are disabled as long as the data is loaded, because we are getting output simultaneously. As soon as the data loading gets completed, all the flip-flops contain their required data, and the outputs are enabled so that all the loaded data is made available over all the input lines at the same time. Therefore, it is called parallel out. So 4 clock pulses are required to load a 4-bit word. Hence, the speed of operation of serial in parallel out mode is same as that of serial in serial out. Shift register, which allows serial input one bit after the another through a single line and produce a parallel output is known as serial in, parallel out, shift register. This is the logic diagram of serial in, parallel out register. We are using serial in, therefore there is only one input and clock is connected to all D flip-flops. There is a clear signal to reset flip-flop. Then here we are using parallel mode. Therefore, we have four outputs, parallel outputs Q0, Q1, Q2, Q3. Here the output Q3 is fed to the input of flip-flop 2. The output Q2 is fed to the input of flip-flop 3 and the output Q1 is fed to the input of flip-flop 4. Suppose we have to store 1, 1, 1, 1. First we are entering the least significant bit. So when we are giving a clock pulse, first bit appears here. When we are applying second clock pulse, first bit shifted to the second flip-flop and the next most significant bit appears here. Third clock pulse, next bit appears here and all other bits shifted one bit right. And after fourth clock pulse, all the bits ended here as 1, 1, 1, 1 and stored in each flip-flops. And in the next clock pulse, we get all data which is stored in the flip-flop simultaneously at the output. Therefore, it is called a parallel output. Serial in and parallel out. So, serial in, parallel out shift register, the circuit consists of 4 D flip-flops which are connected. The clear signal is connected in addition to the clock signal to clear all flip-flops. Output of the first flip-flop is connected to the input of the next flip-flop and so on. I discussed all these things. All of these flip-flops are synchronized with each other since the same clock is applied to each flip-flop. That is all about registers. Thank you.